Okay, so now we have ways to get electron densities. But as chemists and physicists, we really try to think of things in terms of orbitals. Orbitals make more sense to us. We can see what's happening there, and we understand the electronic structure, or we can build towards intuition to understanding that. So what we're going to do now is we're going to have a review of molecular orbital theory. So for us, molecular orbitals, they were something that is mathematical. They were a series of linear combinations of basis functions. We're going to shorten molecular orbitals, or molecular orbital, to MO. How would you describe a molecular orbital? Simpler.
Electrons.
Electrons. What about electrons?
Probabilities. Where they are.
They're a mathematical function to describe how electrons behave in molecules. How would you describe an atomic orbital or an AO? Yeah, in atoms. That's all it changes. Okay, we're going to use some terms that you may or may not remember. Bonding MO. Anti-bonding MO. And non-bonding. MO. Okay, they have different characteristics. One dealing with the energy and the other dealing with what type of overlap you have between the atomic orbitals or your basis functions. Bonding MOs. What would you say about their energy in relation to the atomic orbitals? So we have constructive interference. What happens to the energy? It's lowering. What was that? Yeah. Yep. Lower in energy. And when we say lower in energy, we mean with respect to AOs. Anti-bonding. Yep. Destructive interference. Higher energy. Non-bonding, which we kind of left alone in Gen Chem.
Neutral, right?
Yeah, neutral. No overlap. You went to Ava's thing. Under what pressures?
Under standard pressures.
I'm never going to say never. You can make whatever you want happen sometimes.
We were talking about it about orbital overlap in conjugate systems, Google rule, and all that jazz. So with non-bonding, is that like a where you could have a partial overlap, but it's not entirely constructive, not constructive?
Yes.
was not at that maximum.
Yep. Like, for example, let's say you have a d orbital like this, and you have an s orbital along here. Okay. Constructive overlap here, destructive overlap here. Is there a net gain? No, it's a wash.
Okay.
Or in some cases, you might have like a three-centered bond. There's some character here, nothing there, and some character here. This one's slightly anti-bonding because they're away, but there's nothing, there's not a ton of overlap there. Really, it's kind of a continuum between these, but some people just go, non-bonding.
It's not one or the other, they're in between.
Well, more of like there's no net stabilization or change. Yeah. Okay. Do you want to talk about the types of orbital overlap, or do you want to talk about the rules of MO theory first? Okay. We're going to apply these rules eventually. So the atomic orbitals you use to make the molecular orbitals, AOs in, has to equal MOs out, if we're using a minimal basis set, which we will be when we talk about this stuff. 2, AOs overlap to make what? Yeah. Yeah, MOs. That's an important one. That might have been, probably should have been number 1 over that one. AOs of proper symmetry. Overlap. So if they have the correct symmetry, they're permitted to overlap. If they have incorrect symmetries, they might mathematically not be able to. 4, AOs mix best when close in energy.
Is it like talking about the phase, or is that more talking about like the actual numerical?
More of the overlap, so I guess more of a numerical value rather than the phase. So if you have some things out of phase, if they're in a line, they can actually have constructive overlap. So we'll talk about that later. So that's why I want to use the terms constructive overlap or destructive overlap, because phase is a bit different.
Oh.
Okay?
Yep.
I'm trying not to lie to you as much as I possibly can. Bonding MOs. What about their energy? Yep, then what? Constituent. Six, what about anti-bonding? Yep. And the last rule, seven, ground state structures. Must follow the Aufbau principle. The Aufbau principle is comprised of two other aspects. Does anybody remember what the Aufbau principle stated, or the rules that are contained within the Aufbau principle? It has to deal with how electrons fill.
Is it the Hund's rule?
Yep, Hund's rule is one. And what's the other one? Starts with a P. And an ollie. Yeah. Do you guys want to review those, or do you feel comfortable with them?
Let's do it. I don't remember.
Okay. Let's say, I'm going to use yellow. I have 3 degenerate orbitals, and I have 3 electrons. When I go to fill these orbitals, I know it's already driving you nuts. It's beautiful. Which one's the lower in energy system? Yep, this guy is the correct one. Why? Why? You're right.
Electrons don't do that.
You're right. Why?
Because they're spaced out.
Yeah. Remember, each of these little dashes means a different orientation in space, correct? A different orbital. Here, you've confined 2 electrons near one another. You've also made them slightly different. So you have an exchange penalty here too. Here, they're more spread out, so that Coulombic interaction goes down, and you can't tell, even though I'm calling this guy A, this one B, and C, you really can't tell which one's A, B, and C. Here, you totally go. Which one is this, Hund's rule or Pauli exclusion principle? Oh, this one's Hund's. The Pauli exclusion principle, does anybody remember what that one stated? Has to deal with quantum numbers.
Oh, you can't have 2 electrons that have
Mhm.
quantum numbers.
Yep. Set of quantum numbers. I'm going to label this guy A and this one B. That one A. Yeah, we'll call this one C and D. Even though I'm not technically allowed to label them, I'm gonna anyways, you can't stop me. Yeah. Suddenly we violated everything. Which one's correct? Yes, this guy's correct. Let's write out the set of quantum numbers for A. I use capital A, I didn't. A, B, C, and D. What are the 3 quantum numbers we have that are expressed with letters? N.
Principal energy level.
Yep. What's the next one?
Oh, L.
Yeah. Then.
M's L.
Then.
M's S.
Yeah. Okay. N is the energy level. I've indicated a 1s, so what value would we select for N? Yep. L, the rule with L is a range, right? But here we only have one possible value. What is it? 0. And what type of orbital has an L of 0? Yep. ML also has a set of ranges that could be possible from negative L to positive L. However, we just have a 0. So what's this guy? 0. And M sub S, what was that related to? Yep, spin state. Okay, do you want to call A positive or negative?
Positive.
Okay. So that's the series of quantum numbers describing A. B. Still have to have those 4 sets. It is the same. And that can't be because why? Yep. So wrong.
So would that imply that they're in like the same space? Like I know you can't isolate where an electron is, but
Yeah, they would be in the same area.
Maybe occupying the same orbit.
Yeah. And due to anti-symmetry, you can't do that. Is there a better way to say that?
Not really. I mean, there's no. It is just a quantum phenomenon.
Yeah.
It's just anti-symmetry. It is
Yep.
the nature of Fermi.
Yep. If you're really bored, Richard Feynman wrote a cool short book about it that was very helpful to say why antiparticles must exist and why anti-symmetry must exist. If you're like that sort of stuff, it's a good read. If you don't like that stuff, probably a horrible read. Okay. What number here for C? Yep, 1, 0, 0. N sub S, we said, was plus 1/2. What's going to change for D? Yep, minus 1/2. Okay. Do you feel comfortable that you remember these two things? Okay. Let's draw some pictures of orbitals. Am I cool to erase this? Okay. Let's talk about the types of orbital overlap, because I'm sure it's been a while since that time too. And we might introduce new orbital overlap that you haven't thought about before. We say the type of overlap, sigma, pi, or delta, it's related to the number of regions of overlap. We give symbols to different type of overlap. What types of overlap have you guys talked about in the past? Yep, we're gonna have one other one there. Sigma, sigma star, yeah, they're the same thing. Pi. Okay. I don't know if I talked to you guys about delta. Okay. And then we have N non-interaction. Okay, for a non-bonding system, how many regions of orbital overlap do we have? For a sigma-type bond, how many regions? Pi. Delta. It's 4. I know, it skips that 3. Very irritating. Okay, so let's go at the simplest one that we can think of. And we're going to use a lot in this class. Overlap between oops, a 1s and a 1s. Of course, these systems and orbitals are three-dimensional. We're representing them on a 2D plane, so sometimes it's going to get ugly. The other thing is if I draw an orbital like that, does the orbital only exist here? Mathematically, where does the orbital exist? Everywhere. The orbital technically has a non-zero amplitude everywhere. It gets really, 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 really close to zero. So you can say like it doesn't exist very far, but in reality, it can go much further. We draw these pictures because we can't draw everything. There are some really cool visualization programs like Avogadro, where what it will do is it will show the orbitals as like a fuzzy situation, as amplitudes of maximum density, and you can say, how far do you really want it to show? These are called isosurface plots. So like back when I gave you, did I give you back your daily problems, the graded ones with the orbitals on it?
I think so.
Okay, pull that back out if you have it.
What number was it?
Yeah, that one with the orbital pictures on it. Those are isosurface plots where I've picked just some value I want to represent the molecular orbitals. But in reality, these are diffuse. So some people represent them that way. I wish I would have pulled up Avogadro. Some other people do little fuzzy dots. And you might be able to see it farther away that way. But that actually gives you, oh, it's so loud. That gives you a better picture of what's going on. Okay, let's talk about the overlap between two s orbitals and we'll be done. And next time we will start considering overlap between others. So I'm going to show two nuclei here. Here's an s orbital, here's an s orbital. We sometimes draw them this way rather than the hybridized state. We're going to let them mix and hybridize. And what comes out the other side? Yeah, kind of like an oval. What type of overlap is this? Is this constructive or destructive? Yep, constructive. We call that guy a sigma. Now, so this is a bonding. The energy should be lower. We could have a situation where the basis functions are out of phase with one another. I'm going to show a sign change this way. If I let them mix, what's going to happen here? We're going to get a sigma star, yeah. What's it look like? Yep, right through the center, there's a region where there is no electron density because the orbital overlap. They annihilate one another. Annihilate's not the right word. Cancel one another would be better. More neutrino, yeah. And we could sort of represent it that way. We could have some density in between though. But there is a region where it's a node, or there is none. This guy is anti-binding. Okay, next time we're going to consider the overlap between an s and a p, some p's and d orbitals. Oh yeah.